talk about section 5.4, which talks a lot about vectors. And so let's get a little bit of vocabulary out of the way. And so what is a vector? And so vector is going to have some magnitude and it's going to have some direction. And so some of the common examples where we can see vectors are velocity, acceleration, and force. So for example, we could say I moved a box to the right 5 feet. And so not only is there this length, this magnitude that of the 5 feet, but it also has some direction. It's to the right. Okay, so here is my direction and here is my magnitude. A scalar is just the magnitude, it's just the length. Right? And so some of the examples that we are familiar with are, like I said, length, the area, again, it's just a number, there's no direction, the volume, temperature, and so again, these are going to be real numbers. An example here would be I moved a box 5 feet. Okay, again, it's just the length of this box, of having moved this box, but it doesn't say anything about the direction of where you move this box. And so I moved a box 5 feet. Again, there's only magnitude, there's only length here, there's no direction. Let's talk a little bit more about the properties that vectors have. And so the magnitude of a vector A is written as these two absolute value looking lines and then the A in the middle. Okay, so the magnitude or the length of the vector A is going to be written in this form. Two vectors are equal if they have the same direction and the same magnitude. For example, maybe we have, here is, I'm going to call this vector A here, and then I'm going to call this vector B. Okay, these are equal to each other. Because they have the same direction and the same magnitude. Okay. We also have something that's called the zero vector. And the zero vector has no magnitude and no direction, and it's denoted by a bold zero. And sometimes sometimes vectors have this little line on the top as well. Okay, so this little arrow on top. So let's talk a little bit about what a vector looks like in standard position. So a vector in standard position has its initial point at the origin. And so let's suppose that this is my x and y axis. And so here's my origin. So my vector is going to start at the origin. And then again, depending on what the direction is, then it's going to be either closer to the y-axis, closer to the x-axis. And again, it just depends on the direction of the vector. Let me just draw one just at random here. So I'm going to call this vector u. And so again, its initial position is at the origin here, and it just depends on how long, what the length is, what the magnitude is, and what the direction is. That's going to kind of give us a different kind of vector here. We're going to be able to draw a different kind of vector. And so let's suppose that this vector goes from 0, 0 to some point AB. Okay, so again, the magnitude there. So let me write this down here. The initial point is 0, 0, and here my terminal point is A comma B. So this vector here, we also are able to denote this vector u in terms of its terminal point. And so we can denote the vector as u is equal to these little brackets here, A comma B, these little bracket looking inequality symbols. All right. And so in order for us to denote that this is going to be a vector, we're going to be using, instead of parentheses here, we're going to be using these little fancy brackets here. And so this is letting us know that this vector, its terminal point is at AB. And again, the initial point is always at the origin. All right, so here is my vector u. How are we going to know the magnitude of my vector u? How are we going to figure out what the length of this vector is? So we know that this is AB. So we know that this is A here and this is B. Well, since we know that the length from here to here is A and the length from the x-axis to the point is B, then we can actually use the Pythagorean theorem to find the length of u. So the length between the initial point and the terminal point, again, is the magnitude of u. So again, we're looking for this length here, the length of the vector. And so we could use the Pythagorean theorem to find that length. So let's do that. So we have a squared plus b squared is equal to u squared. That means that we're going to have u is equal to plus or minus the square root of a squared plus b squared. But again, remember, this is a length. Okay, this is the length of a vector, and so we're going to only focus on the positive of my plus or minus. So u is going to equal to, or the magnitude, right, here's the magnitude of u is going to be equal to the square root of a squared plus b squared. So don't forget that we have this little notation here where we trap this little u in these bars here, and that's, again, that means we have the magnitude of a vector. So let me write this down. The magnitude of u, which is equal to AB, is this absolute value looking symbol, okay, which means the absolute value of u, okay, or the magnitude of u is equal to the square root of a squared plus b squared. So again, the magnitude of vector u is these little, this notation, okay, this little u trapped in these little bars is equal to the square root of a squared plus b squared. So if I ask you to find the magnitude of u, I would want you to put the u, the vector u, or whatever vector you're dealing with, and put these little bars around it, these little absolute value symbol, and that's going to equal to the square root of a squared plus b squared. Okay, that's going to denote the length of that. Let's try an example. So find the magnitude of the vector v, fancy bracket 1 comma negative 1 fancy bracket. So we already know that finding the magnitude of this vector is just equal to the square root of a squared plus b squared. So let's just plug everything in there. So my first coordinate here is A. My second one is going to be B. So we know that the magnitude of V is equal to the square root of A squared, which is 1 squared, plus B, with B squared, which is negative 1 squared. So we get the square root of 1 plus 1, which is equal to the square root of 2. So the length of this vector, the magnitude of vector V, is equal to the square root of 2. So suppose we have this vector in standard position. So here at the origin, what is actually giving it this direction? What is causing it to have this direction? Because remember, a vector has to not only have length, but it also has to have magnitude, right? Oh, magnitude is the same thing as length. A vector not only has to have magnitude, which is length, but also has to have some direction. And so what's causing it to have a certain direction? And that what's causing it to have a certain direction is actually called the direction angle. Okay, so what is this angle that's being created between, in this case, the positive x-axis and the position vector in standard position? So here's my positive x-axis, and here's my position vector in standard position, and this angle that's being created from my positive x-axis to my position vector, this angle here, that's what's causing it to have a direction, and it's going to be called a direction angle. And this angle here can be between 0 and 360 degrees. So let's talk a little bit about how we would actually find this direction angle. So again, let's just suppose that we have this this vector here, and let's suppose that maybe it's in first quadrant, and so it stops at the point AB. So this is the terminal point, and of course the initial point is always the same at the origin. So now we're going to have to figure out what this direction angle is. What is this angle here? So let's actually use our trig to find that theta in this case. And so we know that the length here of this side, which is the vertical side here, we know that length is B. So that we know that the length opposite of this angle here is B, and we also know that the length adjacent to this angle theta is little a. So we have this right triangle, and we can actually use one of our trig functions to find the angle theta. So we're familiar with a trig function that has to deal with opposite over adjacent. And so that's going to give us tangent. And so tangent of theta, which is equal to opposite over adjacent, b over a. Okay, and again, we have to make sure that a is not equal to 0 here. This trig function is going to help us find the actual value of theta. And we don't have to use tangent. We can actually use sine, cosine, whatever you want to use. But again, because we just want to work with a and b here, okay, we didn't want to find the magnitude of this vector, then we can just use tangent. But if you find the magnitude of the vector, then you can use the other trig functions. And so tangent of theta is equal to b over a. And if we take the inverse, we will have that theta is equal to the tangent inverse of b over a. And so, again, if you want to find the direction angle, okay, what is that angle that's causing this vector to have some sort of direction, then you can just use tangent. And again, you don't have to just use tangent. You can use sine and cosine, but you would have to find the magnitude of the vector. So let me add that as a note here, just so that you know you have other options. So we can use sine of theta and cosine of theta if we find the magnitude of the vector, which is going to be the hypotenuse here. Okay, so let's try this example 2. Let's make sure that we're really comfortable here. And so example 2 says find the direction angle of the vector u, which is equal to 1 comma negative 1. So that is my terminal point, 1 comma negative 1. Let's graph this. Where's this vector gonna actually, which quadrant is this vector gonna actually live in? And so we know that we always start at the initial point, and then we're gonna go to my terminal point, which is gonna be 1 comma negative 1. And that's gonna put us at the 4th quadrant. And so here's my little vector u there. And so again, we're wondering what the direction angle is. And here's my direction angle. We always start at the positive x-axis, and then we stop at our vector. And so what is this angle here? And some of you guys might be able to tell already what that angle is going to be, but let's use tangent here, the formula that we came up with. And so we know that tangent of theta is equal to negative 1 over 1, which is going to be negative 1. Okay, and so when is tangent of theta equal to negative 1 in the 4th quadrant? Well, if we actually do use the inverse here, don't forget that tangent inverse of negative 1 is going to give you an angle between negative pi over 2 and pi over 2. But our direction angle has to be between 0 and 2 pi, or 0 and 360 degrees. And so tangent inverse of negative 1 is going to give us negative pi over 4. But remember, we want an angle between 0 and 2 pi. So we're going to use its positive coterminal angle. And so that means that theta is going to equal to 7 pi over 4, or 315 degrees. Let's talk a little bit about how we would be adding vectors. And because again, the notation is a little bit different. And so here's the property. If u is equal to, so if vector u is equal to a comma b, and vector v is equal to c comma d, then u plus v is equal to, so it's u plus v, the vectors u plus v is equal to a plus c comma b plus d. And so what's happening is that we're going to actually end up adding the first component, comma, adding the second component. So we're going to add again the first component, and then we're going to add the second components together. So let me just make this clear, this property clear, by doing the example below. So let vector u equal to 1 comma 3 and vector v equal to 2 comma 1. Find u plus v. Then we're going to actually do this graphically, because I want to show you guys how these how the graphical representation of u plus v. And so let's find it first. So we have u plus v is going to equal to, again, the sum of the first components, comma, the sum of the second components, which is going to equal to 1 plus 2, comma, 3 plus 1. So again, we're adding the first component of both of the vectors, and then the second component of both of the vectors. And so u plus v is going to give us another vector, vector 3 comma 4. So let's graph these. Let's graph u, v, and u plus v and see if there's any relationship here. So let's graph u in pink. So again, we always start at the origin. It's going to be 1 My x coordinate is 1, my y coordinate is 3. And so there we go. And that's my vector u. And again, my lines are not the best. Vector v is going to, again, start at the origin and end at 2, comma 1. So that's my vector v. And vector u plus v, I'm going to do it in a soft blue. So again, we start at the origin, and it's going to be x coordinate 3, y coordinate 4. Up here somewhere. And then this is u plus v. You might not be able to see it, but what's actually happening graphically is that if we actually move or vector u so that the initial point is at the end of vector v, and if I move and if I point my terminal point of vector u to the terminal point of vector u plus v, if we actually graphed these two u plus v in this format, we would actually get u plus v as well. And so notice that it actually creates a sort of parallelogram. So if I move vector v, keeping the same magnitude in the same direction, but just moving it above. So again, the initial site is now at the terminal site of my u here. And my terminal site is the terminal site of u plus v. Notice that, again, when I move these vectors, it creates this parallelogram shape. So again, if I wanted to find u plus v graphically, all I had to do was move my vector v. So let me see if I could do it from the tablet here. See if it would allow me to do it, to move vector v. It doesn't want to let me, but it's okay. Let me just show you guys again. So again, if I wanted to show graphically u plus v, I could either move vector v, again keeping the same magnitude, same direction, so I didn't elongate it, or I did not move the direction where it was pointing towards. I just moved it, okay, so that the initial point was at the end of my vector v. Or again, I could move my vector v so that the initial point is at the end of vector u, keeping the same magnitude, same direction, and so it would create this parallelogram. So let me just draw another one here. So if I have vector, let's call this vector a, and I have this vector b here, then vector, I could easily find graphically here vector a plus v. Because again, if I move my vector v or my vector a, I'm going to move my vector a b in this case. I'm going to move it here. So the initial point is at the terminal point of my vector a, keeping the same magnitude, same direction. So here I just transferred my vector v here, and this vector that's being created by using the initial site of vector a all the way to the terminal site of vector v, this vector here is going to be vector a plus vector v. Subtraction works a little bit, it works about the same way. The formula is, of course, a little bit different. So, for example, if we want to subtract two vectors, so if we want to do u minus v, then we're still going to focus on the first component and the second component, but we're going to subtract them instead. So this would be 1 minus 2, comma 3 minus 1. And so vector u minus vector v is going to be vector negative 1, comma 2. So graphically, this would be a little bit different. So if we had vector A here, and we have vector B here, then vector B minus A would actually be this vector that's created in between them. So this would be vector V minus vector A. So again, this would be, again, a graphical representation of what the vectors are actually doing. Right? Let's talk about scalar multiplication. And pretty much what this is saying is that we can actually multiply a number by our vector. So how is that going to modify our vector? So suppose that we have a vector A, which is A comma B, and we multiply it by a scalar k. Remember, a scalar is just a number. And so if we multiply this vector A by this scalar k, then how is that going to affect it? It's going to affect it by actually multiplying each of its components by k, by our scalar. And so our original vector was A comma B, and now the vector has been modified and it has become ka comma kb. So now if k is positive, so if k is greater than 0, then the direction of ka is the same as the direction of A. So what do I mean by that? Suppose that let's suppose that this is my vector A. And if we're multiplying it by a number that is positive, so let's suppose that that k is equal to 2, so we have 2 times A, what's going to happen to the vector is that it's going to double in size. And so it's not changing the direction, but it's going to change the length. And so this is going to be twice the size of my vector A, because again, my k was 2. What happens if my k is a half? So we have 1/2 times my vector, then it's just going to cut it in half. So my vector is going to have half the magnitude as vector A. But again, the direction is not changing. It still has the same direction. The only thing that the magnitude is going to be modified. Okay, so they're still pointing the same direction, but the magnitude is different. But what if k is less than 0? What if k is negative? Then the direction of ka is actually going to be the opposite of the direction of A. So for example, let's suppose that we have, here's our vector A again, and we multiply it by a -1. So let's suppose that here k is equal to -1. And so we're going to have negative A, and now the direction is going to go opposite of, of the vector A. And so it still has the same magnitude. That's not affecting, well, in this case, it's not affecting its magnitude because I'm just multiplying by a negative. So it's going to go the opposite direction. But if I multiply it by, let's say, k is equal to -2, then not only is it going the opposite direction, but I'm also modifying the magnitude. It's going to be double, but in the opposite direction. It's actually going to be a little bit hard to draw this one because I drew vector A so large already. And so it's going to be opposite direction, but double in size. And so I know that's a terrible picture. Sorry about that. Okay, so again, it's opposite direction, and now it's double because k is also 2. Okay, it's 1 -2 in this case. All right, so not only is the direction being affected, but also the magnitude in this case. If k is equal to 0, then we're going to just multiply the whole vector by 0, and it's going to give us the 0 vector. So we're going to have the 0 vector there. Now let's talk about the dot product. So if we have vector A, which is equal to A comma B, and we have vector B, which is equal to X comma Y, then the dot product of A and B is equal to AX plus BY. So what is happening here? Okay. What is the dot product? So what it seems like is that we're multiplying the first components and then adding it to the second component here. So that's going to be the dot product. So AX plus BY. But notice that the result here is going to be an actual number. It's not going to be a vector. And so you have to be really careful that whenever you're computing the dot product, and so it's going to be shown with this little notation with the little dot in between these two vectors, when you're computing the dot product, you're going to end up getting a scalar. So technically this is part of this definition here. Okay. So let's practice everything that we've done so far. Okay, so let's try example 4 here. So it says let W equal -3, 2. So vector W equals to -3, 2, and vector Z is equal to 5, -1. Perform the operations indicated. So for part A, we're going to subtract the vectors. For part B, we're going to multiply vector Z by a scalar, which is -8. Uh, Part C, we're going to not only multiply both of those vectors by a scalar, but we're going to sum them up. And then for part D, we're going to take the dot product of them. So let's start with A. So here's little a. So we want to do W minus Z. And so my vector W is -3, 2, minus my vector Z, which is 5, -1. And so remember, when we subtract these, we subtract them component-wise. And so we're going to have -3 minus 5. And then the second part, the second component, is going to be 2 minus -1 in this case. So that simplifies to -8, 3. And so vector W minus vector Z has created a new vector, which is -8, 3. Let's do B. So we're going to be multiplying vector Z by a scalar -8. So we have -8 times vector Z, which is -8 times 5, -1. And so here, each of the component gets multiplied by the scalar. And it's still going to continue being a vector. So we have -8 times 5, -8 times -1, which is going to give us the vector -40, 8. Let's try C. Maybe I'll use a little bit more colors here. So we want 3 times the vector W plus 4 times the vector Z. So why don't I'll just highlight. So I'm going to highlight 3 and I'm going to highlight 4. Maybe I'll highlight 4 in green. Okay, and so we're going to multiply 3 times my vector W, which is -3, 2, and I'm going to multiply 4 by my vector Z, which is 5, -1. So again, here's my 3, here's my 4. And so first, I have to multiply my vector by my scalar, and then add these vectors together. So let me actually do the work vertically instead of horizontally for this problem. So we're going to have vector 3 times vector W is going to give us -9, 6 plus vector 20, -4. And now we add component-wise. So we're going to have -9 plus 20, 6 plus -4. So this is going to create the vector 11, 2. Let's talk about D. Here we actually want to calculate the dot product of vector W and vector Z. Let me lower this a little bit so it doesn't interfere. So we want to take the dot product, again, of vector W, which is negative 3, comma 2, and dot that with the vector 5, comma negative 1. So remember, we're gonna multiply component-wise, but then add the components together. And so this is gonna be negative 3 times 5 plus 2 times negative 1. And so notice that this is not going to be a vector, this is going to be a scalar. It's just going to be a number at the end. So we get negative 15 minus 2, which is going to give us negative 17. So again, component-wise, so negative 3 times the first component, 2 times the second component. So the second component times the second component of the other vector. So again, here's 3, here's 5, and here's 2 and negative 1. Okay, so hopefully the colors help out. Every single vector is going to have a horizontal and vertical component. And this is actually going to be extremely useful when you get to physics and you're doing Newton's law. And so again, every single vector is going to have two different components, a horizontal and a vertical component. So let me just draw a vector really quickly here. So again, initial is always at, it's a terrible one. So the initial is always at the origin. So here is this vector. So what do I mean by the horizontal and its vertical component? Well, again, if we drop a perpendicular line here, this is going to be my vertical component here, and this bottom one here is going to be my horizontal component. And I know it looks a little terrible here, but it looks a lot better than me trying to draw those curves. So what we're going to do is figure out how we find the magnitude of these horizontal and vertical components. And so we've done this already before. So for example, let's call this horizontal component, let's call this this main vector, I'm going to call this vector W. And so the magnitude of W is equal to R. So this vector W here, the magnitude, the length of this vector is equal to R. I'm going to call this vector down here, and I'm going to try to use different colors. This vector down here, the horizontal component here, I'm going to call that vector WX. Okay, because again, it's the horizontal component of my vector W. And this vector here, the vertical vector, this one's going to be called WY, which is, again, is going to be my vertical component of my vector. So again, I'm trying to figure out what the length of these vectors are. Well, let's use a little bit of trigonometry. So I know that the magnitude, so again here, the length of this vector here is going to be called the magnitude of WY. And the length of this horizontal vector here, that's going to be the magnitude of WX. So again, we have our horizontal vector, which I'm calling WX. The way that we denote the magnitude is by drawing these absolute value lines. The way that I'm going to denote my vertical vector WY is going to be by talking about the magnitude, which is going to be, again, this absolute value of WY. So let me just write this down here. We don't know what the magnitude of Wy is, and we don't know the magnitude of Wx is, but we're trying to figure out a formula that's going to help us figure that out. And again, we're in a trigonometry class, so maybe we can use a little bit of trig. So again, we're trying to find the length of Wy. We know, suppose that we know theta and we know the length of my vector, W, which is r. So the magnitude, the length of my vector is r, and I know theta. So somehow we want to write the magnitude of my vertical and horizontal components in terms of theta and in terms of r. And so if we use again our trig, so for example, the magnitude of Wy is opposite of my theta, and then we know the hypotenuse of or the length of my W here, and so we could actually use sine to find Wy, to find the magnitude of Wy in terms of theta and r. So if I do sine of theta is equal to the magnitude of Wy over, again, the magnitude of my vector W, which is r. Then again, if we multiply both sides by r, we actually have the magnitude of Wy in terms of theta and r, which is equal to r times sine of theta. So we already found, okay, the length or the magnitude of my vertical component. We're gonna do the same kind of idea to find the magnitude of Wx. But notice that Wx is it's adjacent to my angle theta. So we're gonna use cosine. So cosine of theta is equal to the magnitude of Wx over the magnitude of my vector, which is r. So again, if I multiply both sides by r, I get the magnitude of Wx is equal to r cosine of theta. So if I know theta and I know r, then I can easily find the magnitude of my vertical and my horizontal component. And just in case cosine of theta or sine of theta is negative, then we're just going to add the absolute values to both sides. If cosine of theta or sine of theta is negative, then take the absolute value. So for example, the magnitude of Wy is just going to be the absolute value, in this case, of r sine of theta. And again, we're going to do the same thing to the other one. The magnitude of Wx is equal to the absolute value of r cosine of theta. Because remember, the magnitude here, the magnitude is going to be positive. It's the length. And so we want to make sure that r sine of theta is a positive value and r cosine of theta is a positive value as well. So let's try example 5 here. So it's asking us to find the magnitude of the horizontal and the vertical components of vector v. And vector v has a magnitude of 8.3 and a direction angle of 121.3 degrees. Okay, so again, we're given the magnitude, which again in our previous example was r, and we're given our direction angle, which is theta. So again, it doesn't always have to be those letters, but again, since those are the letters that I use in the previous example here, okay, I can just stick to them. And so I have a vector v that has, again, magnitude. So the magnitude of vector v is equal to 8.3. And the direction angle, which I'm just going to use theta just to stay kind of consistent, is going to be 121.3 degrees. So we're looking for the magnitude of my horizontal and my vertical components. Okay, so we know that the vertical the horizontal component of vector v is going to be, we can denote it as vx, because again we're not using w because we're a different vector, my vector v. So vx denotes the horizontal component, and so we know that this is equal to the absolute value of the magnitude of my vector v, which is going to be 8.3, times sine, oh, in this case cosine. So sorry, we're doing v of x. We're doing the horizontal component. So 8.3 times cosine of 121.3 degrees. So that's going to give us the absolute value of negative 4.3. And again, the reason why that number is negative is because this is going to give us a terminal point that's going to be in quadrant 2. Because again, remember, the direction angle is 121.3 degrees. So again, we're going to have my angle here is somewhere in the second quadrant. And so the point there, the terminal side there, is going to be, my x coordinate is going to be negative, my y coordinate is going to be positive. And so it makes sense for this to be negative. And so if I take the absolute value, that's just going to be 4.3. So the length here, the length of the horizontal component, which I'm going to shade here in pink, that's 4.3. And the length of my horizontal, my vertical component here is going to be in blue. Well, we're going to find it next. Okay, so the pink one is my horizontal component, and my blue one is going to be my vertical component. So Vy, again, I'm denoting Vy because again, y represents my vertical axis here. So that one's going to be 8.3 times sine of 121.3 degrees. And that's going to equal to 7.09. And that one's already positive, like I mentioned, because again, we're in the second quadrant where my y value is positive. And again, just doesn't hurt to take the absolute value of a positive number. Right? And so there they are. We found the magnitude of my horizontal component and the magnitude of my vertical component. Example 6 says find the component form for a vector of magnitude 40 miles per hour with a direction angle of 330 degrees. So here, notice that the directions are a little bit different. Here they actually want us to find the component form of my vector. What that means is we want to find the original format of my vector. So what is the actual terminal point of my vector? So remember, component form looks like this. So if we have vector u, we have is equal to some fancy bracket a comma b bracket. And so we're trying to find our a and b here for the given vector with the given magnitude and the given direction angle. So we want to know where is this terminal point that my vector has. Okay, so we always know that the initial point is at 0, 0, but where is that terminal point? So all we're given is that the magnitude is 40 miles per hour and the direction angle is 330 degrees. And so let's, again, they're not telling us what the vector is called, so maybe I'll just call the vector like we have here, let's call it vector u. So again, there's different notation for vectors here. So I'm going to call this vector u, and so the magnitude of vector u is 40, and the direction angle, so I'm going to call that theta, is 330 degrees. Okay. We can actually use the vertical and the horizontal component formula to help us find that point. Because again, remember, if I have, let's say that I have some angle in the first quadrant, just to, again, make things a little bit easier here. So let's say that we're in the first quadrant. And I know that the horizontal component here, that the length here of this horizontal component is actually, let's say, 3. And if we know that the magnitude of my vertical component, if that is 4, then that's going to tell us that my terminal point of this vector is 3, 4. But again, if it's in the first quadrant, then both the x and the y coordinate of my vector is going to be positive. Okay, it just depends on where I am in the Cartesian plane. So since my direction angle is 330 degrees, that means I'm in the fourth quadrant, which means that my my first coordinate is going to be negative, and my second coordinate my first coordinate is going to be positive, and my second coordinate is going to be negative. So let me draw it out. Actually, I think it might be more helpful. So here's 330 degrees. So 330 degrees is about there. So again, I went all the way around here, so that's 330 degrees. So again, notice that this is my vector here. So initial side and end side. We're trying to figure out what is this end point here. What is my terminal point where my vector stops? So notice that we know that point is going to have a positive first coordinate. So let's just call it, so it's going to be positive, the first coordinate. And my second coordinate, my y coordinate here, is going to be negative. So whatever the length is, so here the length of my horizontal component, that's going to be the same as the x coordinate of my point. And the magnitude of my vertical component, well, that one's going to be positive, but if we make it negative, that's going to give us the terminal point here. And so we need to find the vertical and the horizontal component. That's going to give us an idea of where that terminal point is. And then we have to decide, okay, well, which one stays positive, which one stays negative, which we already checked. We already know that the first one's going to be positive and the y coordinate is going to be negative. So let's find these components. So I'm going to find the magnitude. I'm going to find the magnitude of the horizontal component of u, which is going to equal to 40, the magnitude of u, times cosine of 330 degrees. And that's going to give me 40 times the square root of 3 over 2, which is equal to 20 times the square root of 3. Now, okay, again, that's the length of my horizontal component. Now the length or the magnitude of my vertical component is going to be 40, the magnitude of my vector u, times sine of 330 degrees. So that's going to equal to 40 times 1/2, which is equal to 20. So again, this is telling us that the length here, I'm going to call this one, this is in pink here, that the length of the horizontal vector, this horizontal vector here, is 20 square root of 3. Now the length of the vertical component here is 20. So again, we're going to use these to help us find that point. And so that point there, that terminal point, totally misspelled terminal. That terminal point is going to be the x coordinate is 20 square root of 3, and my y coordinate is going to be negative 20. Because again, we're in the fourth quadrant. And the way that we format that it's a vector, that we're talking about a vector, not a point, is we add those little fancy brackets. And so here, we have that u is equal to bracket 20 square root of 3 comma negative 20 bracket. So this denotes that we're talking about a vector here, okay, because we have those fancy brackets. And so this is the component form of a vector with magnitude 40 and a direction angle of 330 degrees. So notice how, again, we used the formulas for the horizontal and the vertical component to help us figure out what that terminal point was, and based on the terminal point, we can actually find the component form from that. Let's suppose that we're asked to find the smallest angle in between two vectors. So if A and B are non-zero vectors and alpha is the smallest angle between them, then cosine of alpha is equal to A dotted with B all over the magnitude of A times the magnitude of B. So if we wanted to find this alpha, okay, so if we wanted to find this small angle here, the smallest angle, then we can use this formula, take the inverse of cosine, and we would find the angle alpha. So what do I mean by the smallest angle? So let me draw here let's suppose that we have the Cartesian plane here, and vector A is maybe in the first quadrant, and vector B is in the second quadrant, let's suppose. So this is vector B, this is vector A. So again, we're looking at the angle, the smallest angle in between them. So here we have, here's one of the angles, so I'm going to call this star. And then the other angle between them is this one, I'm going to call this heart. So which one is smaller? So it looks like star is smaller, and so that's going to be my alpha. Alpha is the smallest angle in between them. Okay, so again here, this would end up being my alpha because that's the one that's smallest in between them. Right? And so cosine of alpha, to find the cosine of this alpha here, again, we're just going to take the dot product of A and B, of the vector A and B, and then divide that by the multiplication of their magnitude. Why don't we try an example? So let's suppose, just to really understand how this formula works, so let's suppose that we have vector A is equal to negative 3 comma 2, and vector B is equal to 5 comma negative 1. And let's find cosine of alpha. Cosine of alpha is equal to the dot product of A and B. So why don't we actually do that first? Let's find the dot product of those first. And so A dotted with B is equal to, again, it's going to equal a scalar. This is not a vector. This is going to be 3 times 5. Okay, so the x-coordinates of both of the vectors plus the y-coordinates plus the multiplication of the y-coordinates of both of the vectors. And so that's going to give us negative 15 minus 2, which is equal to negative 17. Now we also have to find the absolute value, or the magnitude of A. So that's going to be the square root of x squared plus y squared, or a squared plus b squared. So x squared plus y squared, so that's going to be negative 3 squared plus 2 squared, which is going to equal to the square root of 9 plus 4 which is equal to the square root of 13. Now let's find the magnitude of b. It's going to equal to the square root of 5 squared plus 1 squared, which is equal to 25 plus 1, which is equal to the square root of 26. Now let's put everything back together here. So we have cosine of alpha is equal to the dot product of a and b, which is negative 17, all over the multiplication of the magnitude of a and b. Is going to be times the square root of 13 times the square root of 26, which is equal to negative 17 all over the square root of 338. So hopefully that gave you a little bit of an idea of how this works. So last topic that I want to talk about is unit vectors. And so a unit vector, so there's two very common unit vectors. One of them is 1, 0, and the other one is 0, 1. One of them lives in the positive x-axis, the other one lives in the negative x-axis. And the cool thing about these two unit vectors is that we can create any vector by using a linear combination of these two. So any vector that you can think of, okay, with real coefficients here, any vector, okay, if we multiply my vector I and my vector v by some scalar, if I add them together, I get that vector that I'm talking about. So I can create any vector, okay, by doing a linear combination of these unit vectors. So let me just show you where these vectors live. And so again, we have vector I, which is 1, 0. So 1, 0. So again, 0, 0, they all start at 0, 0. And then it's going to be 1, 0. So this here is vector I. Now vector J, again, they start at 0, 0. And the terminal point is at 0, 1. So there's 0, 1. And here is J. Or maybe I'll just do it as little j. So any vector, okay, any vector a comma b can be written as a linear combination of these two vectors. So what do I mean by that? So here's a little definition down here. So if I have a vector a comma b, then we can actually split this up into, again, a linear combination where I multiply my vector I with that the scalar a and my vector j with the scalar b, and I sum them up and I get the vector a comma b, and we can write it as ai plus bj. So again, this is a linear combination. I did forget to mention that the reason why they call it unit vector is because they each have a magnitude of 1. Okay, so again, notice that the length of both of these vectors is just 1. Okay, so let's play around with this this idea of linear combination. And so let's suppose that we have a vector -1, 7. We want to write it again as a linear combination of y and j. So what that means is if we multiply by, again, a scalar and we sum them up or we subtract them, then we're going to be able to get the original vector back. Okay. So again, we have the vector -1, 7. According to the definition here, this is supposed to be, how do we write it as a linear combination? Well, if we do -1, which is again the first component, and we multiply it by our vector I, which is 1, 0, and then we multiply my vector j by my second component, which is 7, this is actually going to end up equaling, and again, remember, this here is denoted as I, this here is denoted as j, and so this is just equal to -1i plus 7j. So -I plus 7j. And so if we do -I plus 7j, if we actually did the computation, we would end up back with -17. So let's just check to just make sure. So we're going to go backwards. So we have negative I plus 7j. And so if we actually expand this out, we get negative 1 times, and remember I is defined to be the vector 1, comma 0, plus 7, which is my scalar, and I'm going to multiply it by my vector j, which is defined to be 0, comma 1. And so now if I actually simplify this, so I have a scalar times a vector, well, we already know that each of the components gets multiplied by that scalar. This is going to equal to the vector negative 1, comma 0, and then the second one's going to end up being 0, comma 7. And now if I add these two vectors, I add them component-wise, and so that's going to end up equaling to negative 1 plus 0, which is negative 1, and then 0 plus 7. Ta-da! We actually ended up getting back the original vector that we started with. And so whenever they ask you to find to write a vector as a linear combination of I and j, they're asking you to write it in this form. Okay, where you have some scalar times I, some scalar times j. You can add them together, subtract them together, and they are supposed to give you the original vector. Alright, everybody, so that is all for today.